good morning, good afternoon, good evening, whatever the time of day it is. It's a good time because we're here with the next installment of the fantastic series of invited talks that we're running as part of the Student Symposium in Combinatorics. Again, I'd just quickly like to thank our sponsors, Matrix, AusterMS, AMSI, and UNSW for all the support that they've given us, which has made this so much more possible to run. Now, it's my great pleasure to introduce the fifth plenary speaker for this series, Jane Tan. So for the Australians in this audience, Jane Tan needs very little introduction. She is very well known and very well liked within Australian combinatorics circles. At the 5th International Combinatorics Conference back in 2017, she received an honorable mention for the Ann Street Student Talk Prize while still an undergrad at the Australian National University, which should give you some idea of the caliber of talk you're about to see. The following year, Jane did her honors at ANU, studying properties of quartic planar graphs under the supervision of Brendan McKay. And after that, she worked as a research assistant for Catherine Greenhill in UNSW for a few months before starting her DPhil at the University of Oxford under the supervision of Alex Scott. If you check out her website, you'll see that she's got many publications currently submitted and in the pipeline around combinatorics and graph theory. From my perspective, it seems like she's writing them faster than people can actually read them. Now, one last thing, I have been told that there are a small handful of people that are specifically here, possibly even at this conference, for the purpose of meeting Jane Tan. Apparently there is some sort of UNSW Jane Tan fan club. So I think it's time for me to step aside, give the people what they want, and let Jane take the center stage to talk to us about reconstruction in combinatorics. Take it away, Jane.
Thank you, Angus, for the very generous introduction. I would love to meet everyone in the audience. I'm not sure about this fan club, but yeah, it's lovely to meet you. And I'm really happy with the chance to speak at the symposium because it's largely Australian, although not exclusively, and because it's such a friendly student format. So thank you so much to the organizers for all their work on this and for inviting me to give this talk. So I will be talking about graph reconstruction today. It's a topic I really like to share, particularly with other students like myself, because it's such a broad area. There are a lot of techniques involved, and it's something you can get your hands on really quickly. So it's just fun to think about. My plan for today is basically to introduce the classical graph reconstruction problem, so we're on the same page. Talk about some of the variants. It's quite interesting to look at the conjectures associated to those, and basically head toward two particular variants that I've been thinking about over the last 2 years, roughly, and get a sense for the kind of flavor of proofs that are used in those. But I'm not going to be doing anything too precisely. I should say I'm happy to be interrupted with questions during, so I think Angus is going to pass on any questions that we spot. All right, so first things first, let's introduce the reconstruction problem. So this is classical reconstruction in the sense that it was kind of the original problem that was defined. So the key definition we're working with here is the deck of a graph, and the definition is up here. It's the multi-set of vertex-deleted subgraphs of a graph G. So in other words, to obtain one element of the deck, we look at a graph, we take one vertex, we delete it together with incident edges, and what remains is one element of the deck. Just in keeping with the terminology, we call each element of the deck card. So you're going to hear that word a lot, cards and decks. And what's really important here is that the cards come unlabeled. So even though I've used this notation for a deck where I've written G minus V for V in the vertex set, when I look at a card, I'm not told what V I'm deleting. That's quite important. Quick example here. So if I take K4 minus an edge, what is the deck? Well, to construct it, so I'm going to take the top left vertex, delete it, that gives me one card. Bottom left, delete it, that gives me a card. Bottom right, delete it, that gives me a card. And the last one, I delete it, and that gives me a card. So abstractly, what I can say is that the deck of this graph, I've called it G, consists of 2 copies of P3, it's a path on 3 vertices, and 2 copies of C3, that's a cycle on 3 vertices. And that is really all we know from the deck. So if we're just given the deck, this is all the information we have in this multi-set down below. We're not given anything above. Okay, so now an important definition, we say that a graph is reconstructible if it's uniquely determined by its deck. So what that means is, just given the deck in this abstract form, we can tell you exactly what the original graph is up to isomorphism. And that brings us to a natural question. So which graphs are actually reconstructible? If we think about this just a little bit, we very quickly find that not all graphs are reconstructible. Maybe I'll give you just a few seconds to think about something that's not reconstructible. So here's the first example, maybe even the first thing you try. If we just look at graphs on two vertices, we have an edge or we have an independent set. In both cases, if we delete one vertex, we end up just with one vertex by itself being a card. So the deck for both of these two graphs is just two copies of a single isolated vertex, and that means that we can't differentiate them. But what's amazing is that this is the only known example of a non-reconstructible graph. So there's a very famous conjecture of Kelly and Ulam from 1941. This came from Kelly's PhD thesis, which was supervised by Ulam. And it states that every graph with at least 3 vertices is reconstructible. This is wide open. So, people have been working on this really since 1941. And while we don't have really much headway into proving this, there are a lot of partial results. So I'm going to bring up a huge list of those here and then unpack them. Typically, when we look at partial results for reconstruction, these come in 2 types. So the first is reconstructing parameters, various graph parameters, that is. So for instance, the number of vertices, number of edges, degree sequence, subgraph counts, connectedness, connectivity, graph polynomials, planarity. So these are things I've put in orange on the page. And these are properties of the graph that we can reconstruct given the deck. The second kind of partial result is classes of graphs that are reconstructible. So for instance, regular graphs, disconnected graphs, trees, unicyclic, outer planar, maximal planar are just some examples that I've put up here. And what that means is that if I have a graph from this class, I can reconstruct that graph exactly given the deck, but it really needs to have the special properties of the class for me to do that. The other result I mentioned is that it's been verified computationally up to for graphs on up to 13 vertices. This was done by Brendan McKay and published actually fairly recently.
Jane, can
improving the previous.
Oh, can I interrupt you for a moment with a question? Tiana from the chat asks, are the cards given so that the position of the removed vertex in each case is observable or not? No, they're really not. So we're just told the isomorphism class of the subgraph that we obtain. So each card is really just it's just a graph up to isomorphism. Thanks. Hope that answers the question. Thank you for asking. That really is important and kind of part of this unlabeled idea. So what I can mention from this page as well is that the difficulty of the results I've listed here really vary hugely. So number of vertices is quite clear because, well, we know how we constructed the card. We just deleted one vertex. So it's one more than what we see in each card. Edges and degree sequence and things like that, they're also very easy to reconstruct. But once we get down to planarity, this is extremely difficult. A similar kind of thing for classes. So regular graphs and disconnected graphs, quite easy to reconstruct. But trees already, it's one of the earlier results, takes a lot of work. Okay. So what I thought I'd do is just give a little example of reconstruction to make sure we're on the same page. So here's a little reconstruction problem. A mysterious person approaches us with 4 cards. Here they are. Each of them is isomorphic to P3, and they require us to reconstruct this graph for them, and or try to help them out. So the first thing we can do is start with some parameters that we know. The number of vertices, we've talked about that. It's just one more than each card that we see, so there should be 4 vertices in the graph. The number of edges is also really easy to obtain. So the way we think about this is if we look at all the cards,
there are 8 edges in total across all the cards. Now for each edge, we know that it should be missing from exactly 2 cards because when we delete one of its end vertices, that edge disappears, but otherwise that edge should remain. That kind of tells us how much we're overcounting here, and that gives us this formula. So we divide 8, which is the total number of edges that we see, by 4 minus 2, where 4 is the number of vertices and therefore the number of cards. And that tells us that our graph should have 4 edges. So we can go further with this. Once we know the number of edges, we can also determine the degree sequence. And that's just because if we look at a card, we know that when we deleted one vertex, the number of edges we're now missing is exactly the degree of that vertex. Each of these cards has 2 edges. We know there are 4 in total, so all our degrees are actually just 2. And well, that's enough now to reconstruct our graph, actually. So let's take one card. We know we deleted some vertex, but we know all degrees should be 2. And now there's only one way to finish this off. And we find that our mystery graph G is isomorphic to C4. So great, we've all reconstructed the graph now. I'm going to take a moment actually to do a little aside and just talk about reconstructing classes of graphs. So in that example, secretly, that's really also just the proof of reconstructing regular graphs in general. But when we're talking about classes, we want to be a bit careful because there are 2 steps involved typically. So the first ingredient that we need is a recognition result. That's something like this. So it says that given the deck of a graph G, we can identify whether G belongs to some class. So for instance, if C was regular graphs, I'd be wanting to show that just given the deck, I can see that the graph is regular. And that's what we did just then, because we had an edge count, and the edge count allows us to determine the degree sequence, and that tells us whether or not the graph is regular. So that's our recognition result. The second part is the actual reconstruction result, but I'm kind of separating these out. So the way I'm thinking of something like this is, given the deck of a graph G, together with the knowledge that G is actually in my class C, we can reconstruct G. So in our previous example, I was kind of thinking of this as, given this deck, together with the knowledge that our graph was too regular, we were able to reconstruct our graph. An equivalent formulation is that no 2 graphs in a class have the same deck. That's essentially what weak reconstruction is. And sometimes we don't really have both of these ingredients for a class that we want, so we end up just showing recognition, which usually comes out as a partial result of the type where we're giving a property that we can find. But sometimes we also get a weak reconstruction result, in which case we're just assuming that we know something's in the class, and that really helps us. So for instance, if you think of trees, that's really limiting how we can glue our cards together to reconstruct our graph, and then use that information to reconstruct. Okay. So this is something I'm going to come back to when I start to talk about a few proofs later on. For the moment though, that was classical reconstruction. Given that we haven't really been able to attack Kelly and Ulam's conjecture successfully, it's really blossomed into this area where there are many variants being studied. And this is natural partly because just in the definition of the classical problem, there are many little things you can change to try and make things more easy or more difficult to try and understand this. But it's also natural just because it's kind of asking a general question about graphs where, what subgraphs actually determine your graph. And there's a nice kind of, just general problem to think about there. So I'm going to split these variants into 2 types. In the first type, we obtain the variant by changing essentially the definition of the card. So I'll just mention 3 of these, or the first one we've already seen. The classical reconstruction problem is also known as vertex reconstruction because we've deleted a vertex in each case. And we saw that the conjecture was that every graph with at least 3 vertices is vertex reconstructible. What we can do instead is actually just delete one edge. So in the edge reconstruction variant, the number of cards in our deck is equal to the number of edges in the graph. And we're just deleting one edge, and that gives us a card. And we do this for all of the edges. And in the same way, these are unlabeled. And as the deck, we just see a bunch of isomorphism classes of graphs. this should feel a little bit easier than vertex reconstruction in a way, because if we're just deleting one edge, I mean, that's less information than a vertex where that vertex might have carried a lot of edges off with it. And in fact, we can show that this is true. So really, if something is vertex reconstructible, it is also edge reconstructible. So this is a strictly easier problem for which we might think, okay, there's some hope of doing this, but we have an open conjecture of Harai from 1964, which is that every graph with at least 4 edges is edge reconstructible. So in other words, the only graphs that are known not to be edge reconstructible have at most 3 edges. And again, we're very stuck on this. Another variant that has a little bit of a different flavor is switching reconstruction. Here the cards are a bit more difficult to define. What we do is, to obtain one card, we look at our graph, pick a vertex, and we switch the neighbors and non-neighbors. So that means if our vertex had an edge, was connected to another vertex by an edge, we would delete it. And if it was not connected to another vertex, we would add that edge in. So maybe it's a bit less clear in this one, but it's also something that feels like it should be easier than classical vertex reconstruction. And that's mostly due to the following image. So say we have our graph and it's switching deck. Take any card from the switching deck and form the deck of that card. So in other words, we look at the card and switch at every vertex again to form another deck. What we know though is that if we switch twice at a vertex, that actually just gives us our original graph back. So if we look at any of these decks of decks, then that's going to contain a lot of copies of our original graph in there. So in that sense, it kind of narrows down the possibilities of what our graph G should be, and it feels like it should be easier. And indeed, we can say a bit more in this case. So there's this result that graphs on n vertices are switching reconstructible as long as n is not divisible by 4. And this funny divisibility condition really just comes from iterating this switching by taking iterated decks. That was proved by Stanley, and also Ulam Coppersmith have a nice argument for that. But again, we're kind of stuck. So from 1985, this variant was introduced by Stanley, and the conjecture, which still stands, is that every graph with at least 5 vertices is switching reconstructible. Okay, so the theme of these variants is that in some sense, we want to make the problem a little bit easier to see if there's anything similar that we can solve. And the answer is typically a no. We can go in the other direction as well and try to make things harder for ourselves. And you might think, oh, why would we do that? But the idea here is if we can show that something, so a parameter or class, is reconstructible from the classical deck, then maybe we could try to pinpoint the minimum information that actually determines that parameter or class. And if we could do that, it would kind of help us to understand where the difficulty is coming from. So this is kind of the idea. The first one is really the most classical variant of this type, which is set reconstruction. So when I first defined the reconstruction problem, I sort of highlighted that this is a multi-set of cards. So the multiplicity is important. In this variant, we're just taking the set. So we lose the multiplicity information, but everything else is the same in terms of deleting vertices. Unsurprisingly, there's an open conjecture here that every graph with at least 4 vertices is set reconstructible. Apart from set reconstruction, though, there are other incomplete decks we can take if we're given a little bit more information. So for example, we could consider reconstructing trees just from the cards associated to deleting leaves. And that can be done. So that was shown by Harai and Palmer in 1966. Something more general is called the reconstruction number. And this is essentially the number of cards, well-chosen cards that you can take from the deck that determine the graph. So in other words, you'd say, maybe we have the deck and we're trying to pick out the smallest number of cards that we actually need to reconstruct the graph. And a really nice result of Bolabash from 1990 states that almost every graph has reconstruction number 3. Almost every here is in a probabilistic G, let's say G and half sense. It's actually okay if P is not really a half here. And what this is saying is that almost every graph in that sense has 3 cards which actually determine it. And in fact, this proof goes even a bit further and says any 3 cards would determine almost every graph, which is quite incredible. On a similar theme to this, so the 2 variants I'm going to talk about are to do with missing cards and small cards. Missing cards is basically this, except that we don't get to choose our cards carefully. We're just, we've just lost some cards and we don't know what they are. So we have to work with the worst case scenario. And for small cards, well, I'll come to that in a second, but essentially we define our cards a little bit differently so that we're deleting more vertices at a time rather than just one. So for the rest of the talk, I'm going into these 2 variants. Let's start with missing cards. So we've seen now from the full vertex-deleted deck, we can reconstruct a bunch of things, including a number of edges, connectedness, planarity. So the question here is, what happens if we're missing some cards from the deck? Or equivalently, so say if we're missing K cards, what we're asking is, what can we reconstruct given any n minus K cards from the deck? A little bit of history. So in 1988, when de Moerveld showed that we can determine the number of edges of a graph from any n minus 1 cards, that actually already takes a little bit of work. It wasn't until 2018 that this was improved to n minus 2 by Brown and Venner. And then there was some further improvement in 2021 by Honland, Kugiari, and Scott, showing that it's enough to have n minus root n cards, so we can delete about root n cards. In some work I did with Carla Honland, Tom Johnston, Andrei Karpowski, Kitty Meeks, and Alex Scott, we showed that if we add an extra assumption that we have a bounded average degree, so average degree bounded by D, then we can still get the number of edges even if we delete a linear number of cards. So I think this is going to be the first proof that I outline today. So very much strictly an outline, but this is roughly how it goes. So this is how I'm viewing my deck. The grayed out cards are things that I'm thinking of as missing, although I don't actually know where they occur in my deck. I am ordering the cards by decreasing number of edges. So that means G1 has the most edges and Gn minus K has the least number of edges, where K is the number of cards that I'm missing. And equivalently, another way to think of this is that I'm ordering the cards by increasing degree of the vertex that I've deleted. So this is completely equivalent. So the first thing we can do is we can recognize the bounded average degree to a possible error of 1. So in this statement, I'm not assuming that we know this D to start with a priori, but we really obtain it through the proof. So the way to do this is roughly to do something like the edge counting argument we saw earlier, except that we only see a subset of the cards. So we have to account for the fact that we're not seeing all of the edges. But nonetheless, that's actually good enough to get this bounded average degree pretty close. So D tilde is the notation I'm using for the estimate here. Then what I do is we focus on G1, that's the card with the most number of edges, and that provides a first estimate for the total number of edges in the graph. It's really the best estimate that we have immediately, I suppose. Now, this is where the bounded average degree is useful, because given that the average degree is bounded, we can show that there have to be quite a lot of vertices that have smallish degree. Right? This is kind of just because we have an estimate for the average. But what that ensures is that the degree of the vertex we deleted to obtain G1 has to be quite small, even if all of these grayed out cards occurred before G1 in this ordering. Nonetheless, this degree has to be reasonably small. So that's kind of why we need the bounded average degree here. And then what we can show is that within G1, there's some T such that there are a lot of vertices with degree T. And that's going to allow us to basically find a card later in the ordering that has degree exactly T. So let me qualify the many here first. By many, what I mean is well, how can we lose vertices of degree t? So one way is that, well, we might be missing those cards corresponding to vertices of degree t. So we need to make sure there are enough so that when we're kind of counting forward from G1, we're actually going to have a big enough range of things corresponding to vertices of degree t that we can pick out a card exactly. And the other reason we can sort of be off in this count is that if we delete the vertex, so let's call it V1, to obtain G1, that vertex might have been incident to things that were degree t, but that's deleted, so they're now degree t minus 1. So we kind of have to account for these two possibilities, and that's why we need an estimate here. But essentially we can get around this and find a t such that by counting forward a certain number of times, and that number of times we can determine by looking at G1, it's basically the number of vertices with degree smaller than t, we can find a card corresponding to deleting vertex of exactly t. And then we're done, because the number of vertices in the graph at this point is the number of edges in the graph at this point is the number of edges that we see in whatever card we've landed in, plus t, which is the number that we've deleted. Okay, so that's just a little sketch of the proof and this idea of kind of coming up with an initial estimate, working with that estimate and kind of propagating it down. So just a note that once we've actually done this proof, we started with this estimate d tilde, but by the end, we now have the number of edges exactly, so we can actually reconstruct d exactly. And this is kind of important to proceed and use this. Okay, so the reason I note that is we have this result that n-1 cards determine the number of edges. Actually, it's then easy to deduce that n-1 cards determine the degree sequence in pretty much the same way as we saw in our example. So we just look at the card and subtract the edges we see from the total number of edges that we know. When we are missing one card, but that's not really an issue because we have this handshaking lemma that twice the number of edges is the sum of the degrees. So we can use that formula to find out the last degree that we're missing. That's fine. What we're able to show though with the same group of co-authors is that again, under this assumption of bounded average degree, although I've written it here as embeddability on a surface, it's just a nicer statement. Again, we can reconstruct the degree sequence from any cards, any deck where we're missing a linear number of cards even. So again, just a little sketch of this result. It's not so simple here as with n-1 cards because we don't have this exact theorem which will spit out the last value for us. But instead what we have is this relationship, which is quite easy to show. So here I'm using d sub t to denote the number of vertices with degree t in whatever graph. To get the degree sequence, I just need to tell you what d sub t is for each t between 0 and n-1. So that's the goal. But there's this easy relationship that if I look at the total number of vertices with degree t in all of the cards, where do they come from? Well, the first possibility is that they actually had that degree t in the original graph. And when we deleted a vertex to obtain a card, it wasn't touched. That's fine. The other possibility is that it was a vertex of degree t plus 1 in the graph, and we deleted a neighbor of that vertex, so that dropped it down to degree t. But these are the only two possibilities, so we get this equation. What we can do then is reconstruct an estimate for this quantity up here. I'm just going to call that st tilde. We can then rearrange this quantity up here and substitute in the estimate to get an estimate for dt in terms of dt plus 1. That's kind of interesting. And then moreover, what we can show is that this estimate actually has error less than a half. And this is key in a way because, well, it's also kind of cute. Because we're working with integers everywhere, all of these values are just counts for numbers of vertices. As soon as our error is down to less than a half, we can round it. And once we round it, that actually gives us the exact answer. So that's how we kind of get rid of the error in this result. So then to actually do the proof, so here I've written dt in terms of dt plus 1. You can also imagine we can run this the other way to get an estimate for dt plus 1 in terms of dt. In the proof, how this works is we consider d0 up to dn minus 1, which we want to work out. We show that there's actually one value that we can determine exactly, somewhere in the middle of this range. In fact, it's going to be a 0, it just happens to be. Now what we do is, say this is our dt plus 1. We're going to substitute that into this estimate to obtain a dt tilde. But we know that the dt tilde is within less than a half error of the actual dt. So we round it, and that gives us dt exactly. So what we've just done is, using dt plus 1, we found dt. And similarly, using dt, we can find dt plus 1 just by rearranging these equations around. So we kind of use this method of pushing to obtain d9, d10, d11, d12. And once we've done in one direction, we can also push the other way to obtain all the degrees the other way. And once we have a picture like this, where we know the number of vertices of each degree, that is actually our degree sequence. I should mention that this method of pushing was really already used by Groenland, Gugliari, and Scott in the earlier paper, where they found reconstructed the number of edges. Okay, that's a summary there. So that's all I'm going to say about that particular proof, but there's a kind of frustrating open problem. Here, for both of these, I had to assume a bounded average degree. We can't get around that. But there's a kind of embarrassing question that we can't answer, which is, can we reconstruct the degree sequence from n-2 cards in general? So n-2 is the first place where we lose this nice relationship that allows us to, just sort of fill in one or more card using handshaking lemma, and we just can't do it. So yeah, it would be a great one. I mean, surely the answer should be yes. In general, it's conjectured that for n large enough, we should be able to reconstruct the degree sequence from n-k cards, certainly. But yeah, that's something that's difficult at the moment. I'm going to leave missing cards there now and move on to the second variant. This is the small cards variant. So this one was introduced by Kelly in 1957. It was actually kind of just slipped into a paper where Kelly was proving that trees are reconstructible in the classical sense. Kind of just made this definition as well, but didn't do too much with it, and seemed no one really picked up on it until 1974, when Manville came along and suddenly proved a bunch of properties using this definition. So the main idea here is that instead of just the deck, we look at the L deck of a graph G. And this is the multiset of all induced subgraphs of G on L vertices. In other words, if we kind of flip it around, it's the multiset of all subgraphs obtained by deleting K vertices and all incident edges. So the first thing to note is that the classical deck of a graph that we've seen is exactly the n-1 deck here, so dn-1, where n is the number of vertices. Here's a general tool. So anytime we're looking at reconstruction problems which involve the full deck that are defined in some way like this, there's a really important lemma of Kelly, which goes as follows. So if we take some natural number L and let H be any graph on at most L vertices, then for any graph G, we can reconstruct the number of copies of H in G. It doesn't matter if that's induced or not induced, we can choose. And in particular, it's just given by this formula. And the proof is extremely easy. It's actually exactly how we counted edges before. So all we do is we count the number of copies of H that occur in all of the cards. That's our numerator. And on the denominator, I'm just dividing by the number of copies, by the overcount, essentially. So how many ways are there to kind of destroy a copy of H? How many we should be missing? And this is n minus the number of vertices in H, choose L minus the vertices in H. But really, it's just generalizing this edge count result we had earlier. What this shows in particular, though, is that if I have the L deck of a graph, it determines the L-1 deck. right? Because if I'm given the LDEC, I can look at all graphs on L-1 vertices, run Kelly's lemma. That tells me the number of copies, but that's actually just the multiplicity of this graph as a card in the deck, in the L-1 deck. So given that, it makes sense to think for a parameter or class that's reconstructible from the deck, what is the smallest L for which it's also reconstructible from the L deck? So in this sense, we're limiting the information we have. Okay, let's look at a few things that are actually reconstructible in this way. So from the 2 deck, which is not a lot of information at all, we can still reconstruct a number of vertices and edges, which is very interesting already, because for missing cards, we were working hard to reconstruct the number of edges. And here, because it's exact in a sense, there's a very different feel. We can use these exact counting arguments and do this directly using Kelly's lemma. After that, though, we're quite limited in results, mostly to the N-2 deck. So this paper I mentioned of Manville, who kind of reintroduced the notion of LDECs, proves that we can reconstruct connected graphs, acyclic, bipartite, regular, and unicyclic graphs. We can reconstruct those properties from the N-2 deck. And since then, there's been quite a lot more work on this. So the degree sequence can also be reconstructed from the N-2 deck, and that was improved to N-3. There's some better asymptotic results. Similar things to do with connectedness. Giles showed that trees can be reconstructed from the N-2 deck. And a computation result is that McMullen and Radzizowski showed that every graph between 6 and 9 vertices is reconstructible from the N-2 deck. One final result, 3 regular graphs are reconstructed from the N-2 deck. So that's a more recent result. So I was working on this again with Carla Honland, Tom Johnston, and Alex Scott. And we were able to show some results where we're really deleting much more than 2 cards. There are 3 in particular that I'll mention. So the first is that for n at least 3, we can reconstruct the degree sequence for any L deck, given that L is at least root 2n log 2n, so roughly root n log n. And that's improving upon the N-3. That was the last exact result from Kostoshka, Navi, West, and Zerlin. For connectedness, we show that this can be reconstructed provided L is at least 9n on 10. So that's really going down to linear, which is an improvement from, again, N-3 from the same authors. And finally, we show that any tree is reconstructible from the L deck whenever L is at least roughly 8/9 n. And that's an improvement from just a constant N-2 from Giles. What's interesting, though, is that there are some quite different proof techniques here. So in the last sort of 10, 15 minutes, I'm going to just outline some of those techniques. Let's start with the degree sequence. So here's that result again. The degree sequence of an n vertex graph can be reconstructed from L for any L at least roughly root n log n. So funnily enough, what we use here is an algebraic tool, and it's this theorem, which we shouldn't look too deeply into. It gives a bound on the number of roots of a complex polynomial, essentially, a number of positive real roots. Just looking at this, it's quite surprising and really lovely that something like this could be used for reconstruction. The form that we actually end up using it in, so this is the original by Bowen, Erde, and Koch. The form that we use is a rephrasing by Bowen and Ingalls, which is to do with moments of sequences. So it's completely equivalent, and it says that, so 2 sequences, which are not just a permutation of each other, have to be, well, if they're moments, by which I mean this, so you take the, sums of the these binomial coefficients, and this gives you your jth moment. If all of their moments agree for at least r plus 2 of these, then actually those sequences have to be the same. So this is a result on how many of these moments can be shared between two distinct sequences. The way we use this is as follows. So the idea is for our sequences, we're going to take the degree sequence. Not related by permutation is good for us because our degree sequence we should not think of as ordered. And we're going to set these alpha I up here in our sequence to be the degree of the vertex I. So it would really be enough if we could reconstruct these moments somehow from the graph. But it turns out that's really easy to do using Kelly's lemma, because all we have to do, I claim, is count the stars of all sizes up to k1 l-1. So a star here is just one vertex. The second parameter, so l-1, is a bunch of leaves, and we join the central vertex to each of those leaves. Like that gives a star. I mean, why does this work? Well, if we think about this sum, so we're looking at all of these coefficients, all we're doing is we're fixing, so if we look at a particular summand, we're fixing a vertex and looking at its degree, and we're looking at the number of ways to choose j of those leaves. But if we choose j of those leaves, that actually determines a star with j leaves, which comes with center at this vertex. So in other words, we can think of this sum as just counting the stars with a center at a particular vertex. And in that sense, Kelly's lemma really reconstructs this for us. That's pretty much the entire proof. So this root 2n log 2n we can see matches exactly what's going down here in the theorem. Okay. That's all I want to say, I think, about that algebraic method. It's just something quite fun. For connectedness, the proof is actually very similar. So it uses the exact same algebraic tool. Instead of looking at degrees of vertices and those stars, though, we define something that's just slightly more general, where we look at kind of the degree of a subgraph. So if we view a subgraph as a ball, we look at leaves hanging off this graph and apply a similar method there. So I'm not going to prove the connectedness, but I would like to move on to the trees a little bit. So if we specialize to tree, there's a conjecture of Niddle from 1990, which is that trees with at least 6 vertices are reconstructible from the deck whenever, from the L deck, whenever L is at least n on 2 plus 1, so roughly n on 2. That's quite a bold conjecture, given that all the results we've seen, specifically or especially pre-1990, are just for at the n-1 deck or something like that. But there are examples that would make this tight. So I think you can take a path with one leaf hanging off the middle versus the path with one leaf hanging one off the middle. Okay, so this is the result that we're able to show. So we can actually reconstruct whenever L is at least 8/9 n. So in some sense, this is, right up to a factor, right? Previously, we'd only had constant, so this is quite an improvement. And this is basically how the proof goes. So again, we have this issue of recognition, weak reconstruction. The recognition I'm going to skip over a little bit. So we're able to show that you can recognize a tree whenever L is at least 2n plus 4 and 3. At the same time as we were writing our paper, though, Kostochka, Navi, West, and Zerlin showed that you can recognize the tree whenever L is at least n on 2 plus 1, which is really nice. So that matches Niddle's conjecture and really reduces the conjecture now just to a weak reconstruction problem. Let's talk about weak reconstruction for this 8/9. The way we do it is we split it into 2 cases. There's a high diameter and low diameter case. We use a different counting tool for each one. So for high diameter, it's something we call extension counting. That's something new that we came up with. For low diameter, there's a nice standard tool called the Grimo-Heminger theorem. And this essentially counts maximal subgraphs. Without going into any detail, really, the key thing to know is that both of these are heavily based on Kelly's lemma. So that's kind of underlying all of the methods here with exact counting. I think I have a couple of minutes, so I'll just try to outline maybe the high and low diameter ideas. So what we want to do, the reason why diameter is interesting is that it can help us to provide an anchor, which allows us to glue parts of the tree together. So in the low diameter case, what low means is that it's small enough so that we can see the longest path on a single card. that's really useful because the center of a tree, whether that's a vertex or two vertices, is unique. So regardless of the longest path, that center is going to be well defined. And that gives us a place where we can kind of cut up our tree and try to count things around it. So if this is the tree we're looking at, what we do basically is try to reconstruct all of these branches that come off the center. And I'm using colors here to roughly indicate isomorphism classes. What we need to know is really the isomorphism classes and multiplicity of each isomorphism class for a branch of the center. So this is really easy. If there's only one unique longest path, then we just have to count maximal copies of these two things. So draw them as paths with blobs. But essentially, this is a longest path that I'm thinking of on the horizontal that provides an anchor. And then we know then that anything that's coming off in this little balloon here is really one of the branches that we're interested in. And similarly, we have branches that might contain half of the longest path, so we have to account for those. Maximal here is important because if we go back to this picture on the right, imagine this red, for instance. This red branch is a subgraph of the blue branch. We don't want to count this as multiplicity because it's not actually another separate branch on its own, which is why we need maximal copies. So that just means we can't extend it to any other of the branches that we have. Okay, I mean, that's the easy case. The slightly harder case is actually not much harder. All we're doing is we're going to count every possible rooted tree, so rooted tree B, that's a candidate branch, once for every longest path. And there's just a little formula here which tells us how to do that. So again, for every longest path, we get these branches. Those ones are quite easy. If our branch actually includes half of the longest path, then we just need to count these kind of lollipops where we have half a branch plus half a path, and then the number of ways that path can be inside our branch. Okay, that's roughly the low diameter case. And very quickly for high diameter. So here we need to do something different. And what we're exploiting is that if we have a tree and delete any edge, that gives us two components. We call them R and S here. And they're kind of bridged by the single edge. So it would be equivalent to reconstructing the tree if we could determine a pair R and S such that they glue together to form our original tree. And we know exactly where to glue them together. So the problem kind of becomes, how do we identify such a pair? And how do we test that the gluing actually forms our original tree? We call these leaf extensions, and we come up with a whole kind of extension counting lemma to deal with these. I'm going to skip the actual counting, but the idea is that we can find candidates for R and S just by running through all possibilities where the neighborhood of this subgraph within the tree only contains one extra edge. And that's important because that tells us where we can glue them together. Now, to test whether they actually form the correct tree that we want, what we do is, well, say R is smaller than S, we look at the number of copies of this extension, so R plus an edge, inside T. And I claim that that's always either equal to the number of copies in S, or it's equal to the number of copies in S plus 1. Right, so I have all these pairs which may or may not glue to form the tree. If all copies of R are already in S, then okay, that's not a good pair, so I reject it. But if I find a pair that actually gives me this number of copies of R in S plus 1, then I know that this has to glue properly, because the only place that plus 1 can come from is if it's the other side, essentially T minus S. So that's roughly how we do the testing. Okay, I think that's all I'm going to say about these proofs. The general idea here is that for these ones, there's really a lot of exact counting and playing around with substructures to see what we can get out of it. So the lemma that we form is really is what allows us to sort of determine these numbers of the extensions that I'm using in this formula. Okay. So I'm just going to include with a couple of problems, and there are many, many problems left over, but I'll try to specialize to a few. One is this conjecture of noodle, which feels like we're reasonably close to at this point because we're down to linear. Unfortunately, in the process of actually proving that, Tom, one of my co-authors, showed that the conjecture is not true as stated. So there's a counterexample, which are just these two graphs. These are non-isomorphic trees on 13 vertices, and they have the same 7 deck. That is hard to check. He really did this by computer. So a natural question is, does Noodle's conjecture maybe hold for n greater than 13? So there's still a hope there, but we're not exactly sure. We spent some time trying to generalize this counterexample to find something larger that would help us disprove it, but that hasn't really worked out. I think there's still some hope though that this n-2 roughly might be correct. More general questions. So are planar graphs reconstructible in the classical sense? That's something we don't know, and seems very difficult. So we already have the recognition result, but in terms of reconstruction, seems like it might be quite difficult and require something a bit new. More generally, a lot of the results I've mentioned just have huge gaps. So for instance, with the small cards or with the missing cards, none of these results are really tight. We're trying to work on going from missing constant cards or deleting constant number of vertices just to something that's linear even. And these are big steps, but we don't have tight examples for many of these. And I've already mentioned this n-2 question for degree sequence. So if can we reconstruct the degree sequence of any graph from any n-2 cards? But yeah, there are many questions in this area, and I just really like how broad and how varied it is, how easy it is to get your hands into it. I think I'll stop there. Thank you very much.
Thank you, Jane, for a fantastic talk. Everyone give a virtual round of applause. Are there any questions from the chat? There was a Q&A a few minutes ago, but it just says, "Hi, Jane." So if someone got halfway through their question, please submit the rest of it. But I've got one question to kick it off, maybe. The thing you mentioned just before about the conjecture for recovering the degree sequence from an n-2 deck, and you said that's a conjecture. Are there results that go the other way that say if you've only got like a half n deck or something, you can't get it back? Is there anything like that?
Yeah, so there are some bounds like this. I'm not actually sure exactly for degree sequence, but I think for reconstructing graphs in general, we're looking at something like 2n on 3. If you consider paths, the examples usually come from looking at disjoint unions of various paths and stars. Okay. You can kind of see how that works. So you delete one, you get a path out the end. And that's the lower bound for reconstructing the graphs, and therefore for degree sequence as well. Quite likely there's something better for degree sequence that I'm not sure of.
That makes sense. Thanks. Someone also asked, is there any algorithmic study for any of these problems? Could you suggest some sort of survey paper about this?
Algorithmic studies? Actually, not so much. I think, so a lot of the methods we're using are not very algorithmic in the sense that, anytime we're doing these counting arguments, we're really assuming we're using big numbers, and the bounds are not very good and not very optimized. I guess the main thing for algorithmic studies would be papers like those of Brendan McKay and Razovsky that I mentioned earlier, which are verifying the conjectures up to a certain point. For that, they use a lot of the standard kind of generation techniques. So I might recommend looking at those papers. You're welcome to message me, and I can ping you the papers if you like afterward.
Excellent. Tiana has a question of, are there any sort of interesting variants where you add things to the cards? So where somehow additions, like adding extra edges or vertices, are made to the original graph on each card?
I haven't actually seen a variant of that. So I'm not immediately sure if some variants of that would be trivial. I guess I'm imagining, take a graph and add an edge in all possible ways between two non-adjacent vertices or something like that. I would have to think about that, but I'm not sure. I haven't seen it. I think the reason why it's quite natural to be removing information is just because of this general philosophical question of which substructures determine what we have. It's possible that adding is also going to be difficult. So a graph is reconstructible if and only if its complement is reconstructible, and that might handle some possible additions that you can make here. But apart from that, I would have to think about it.
Thanks for that. Are there any other questions? Maybe time for one more.
There's one in the chat.
There is one in the chat, yes. Thank you. Chromatic number or bipartite, are those properties reconstructible from the, or is there anything known about it? Reconstructibility for them?
So we had chromatic polynomial that would tell you something about this. So I guess that gives you some information about this. I'm not sure what the best result would be for just for chromatic number.
Okay. Yeah. Cool. Thanks. We might wrap up questions there, but I'd like everyone to just give one more round of applause for Jane for a great talk.
Thanks very much.